Okay, hi everyone. So in today's session, I'll be taking you through something called as a kernel. A kernel is a topic related to support vector machine, and trust me, this is one of the most ambiguous topics which I would have ever studied in SVM, right, in machine learning. And till few days back, I would say that I was still not very sure about what the kernel is, what exactly is the use of it, right? If you were to ask me frankly, but then with the help of ChatGPT and some more research, I was able to finally decode that. So I thought, okay, it's apt time that I also try to delve into what a kernel is and help people understand what exactly it is, right? For those who are not very familiar with or who still struggle to understand what the kernel is, right? So let's get started without any further ado. So here is this thing, okay? So let's imagine we have point like this, okay? We have, this is our x-axis, this is y-axis, okay? And let's say we have points such as, let's call it 1 0, the other point let's call it as 2 0, okay? So this is a, this is, let me call this as b. So let's say this is minus 1 0, this is b, let's call c, this is c, and let's call it as d, okay? And there is nothing but 2 comma minus 2 comma 0. Now imagine uh, due to one in one classification, point A and B belong to the same class, okay, and they are nothing but they belong to plus one class, okay. This is plus one, this is plus one, okay, and then this is what, this the other 2 points, that is minus C and D, belong to the negative class, that is minus 1 and minus 1. All right, now have a look at this. These two belong to the same class. A and B belong to class 1, and then C and D belong to class minus 1, right? Now if I have to think of it, there is no linear separation. There is no linear separating plane which can separate AB into one cluster and CD into one. So let's try with this. Okay, so if you try like this, it won't be possible. If you try like this won't be possible. The only way, or let's say the only way which can separate these points, okay, just a minute. Okay, so as I was saying is, the one of the ways in which we can separate is these points is nothing but a non-linear decision boundary, okay. So let's call it as 1 0 as it was earlier 1 0. Now this is 2 comma 0, okay, this is minus 1 comma 0, and this point is nothing but minus 2 comma 0, okay. So if I have to look at this, if we have a decision boundary which is circular, okay, this can separate. So it will separate point A, B with point C and D. Okay, but as you see, this is non-linear. This is not a straight line. This is a curved, right? So therefore, one of the ways in which we can separate these points A, B, C, and D is using a non-linear boundary. But as we have seen, our typical SVM, okay, as you would know, the dual optimizer, right? We can write it as alpha I minus alpha I, okay, alpha j, then xi, sorry, yi, yj, okay, and then we have something called as xi transpose into xj. All right, if you look into this is the linear separation plane, right? This only accounts into the segregation of those points which can be separated by the linear boundary, but this is not applicable to this, right? So how do we actually make SVM work for this? So one of the ways is, let's do this thing, okay, let's create a transformation, let's create a separate feature. So right now we just had x and y, okay, so what we will also do, add a third dimension to it and call it as x square plus y square, okay. So our initial point was a, which was nothing but 1 and 0, okay. Our point b was nothing but minus 1 and 0, okay. C was nothing but 2 comma 0, and D was nothing but minus 2 comma 0. So what we'll do is, now the transform point, let's call it as A dash, becomes what? It becomes 1 0, and then 1 square plus 0 square is nothing but 1. B dash becomes nothing but minus 1 0, x square plus y square is nothing but 1. C dash again is nothing but 2 comma 0 comma 4, okay, and d dash is nothing but minus 2 comma 0 comma 4. So what I have done, I've created a third dimension to it. So our point was initially 2D, but I have created a 3D, and if you were to look at it, it would look like this. Okay, so let me go to the XYZ axis and let me show how it would look like. Okay, so let's consider it to be Z axis. Okay, this one is X axis, this one is Y axis. Okay, so this is X, this is Y, and this is Z. Okay, now our first point becomes 1 0 becomes 1 0 0 1. Okay, so this is 1, this is 0, and this is nothing but 1 0 1. Okay, so this is our A dash. Okay, similarly, what is our B dash? Minus 1 0 1. Minus 1 0 1. So if we are to push it back like this would become a negative x axis. Okay, now this would be nothing but minus 1 comma 0 comma 1, right? This is in the negative x axis, this is 0, and this is in the z plane, right? Xz plane. So we have this is negative x. Okay, so these are become 2 points. The other 2 points are 2 0 4. Okay, so this is A, the second point over here 2 0 and 4, so it would lie somewhere over here. Let's call it C dash. It is nothing but C dash is 2 0 4, and D dash would be over here, right? Minus 2 0 4. So let me redraw this. So our first point was over here 1 comma 0 comma 1. Okay, the second point minus 1 0 1, right? So this is A dash, this is B dash. Now C dash is what? C dash is called as C dash. This is 2 0 comma 2 comma 0 comma 4. Okay, let me even write this. Okay, and then this point is I think okay, here it would be, it becomes minus 2 comma 0 comma 4. Okay, so now you see, by using a third dimension of x square plus y square, okay, we are able to create, or let's say we are able to actually put these points into higher dimension. Initially it was in 2D, now we have put it into 3D, right? Such that these points, okay, can be segregated by a particular plane. So this was, let's say this is one classification, okay, this is plus 1 class. Alright, these two are C and D over here belong to minus 1 class, okay, right? So we can have a plane something like this, okay, which separates these 2 points. Okay, so this is our D, this is C, this is B dash, this is A dash. So again, let's go back to the initial scenario. The initial scenario was these all points A, B, C and D were 2D, right? So it was not possible to separate them using a linear decision line. But if we put them into higher dimension, what would that do is put the points into higher dimension at a higher space at a different altitude, okay, which then enables us to separate these points using a hyperplane. Now just please remember that we are all talking into 3 dimensions or higher dimension. This is not in 2D. You can't separate these two using a linear boundary in 2D, but using a if you put them into higher dimension, right, you can separate them using a plane, which I have shown over here, right? This is what it is, and you know, this we represent this adding a third dimension. So this is what adding one more feature, adding more feature to the given points. This is what we have done, right? To enable us to separate these points using a linear decision boundary at a higher dimension, not in 2 dimension but a higher dimension. This is what we have done, right? This is nothing but a decision boundary at the higher dimension. Okay, so let me write the formula what we initially had into higher dimension, right? So what we had written was initially, okay, this is our 2D thing, right? So what we had alpha I, okay, let me also write j, okay, so we had alpha I, alpha j, and then we had over here yi, yj, okay, and then we had xit into xj. This is what we had, okay. So what we have done is we are saying that let these all things remain same, okay, but instead of xi, all right, which is let's say xy in our case, we represent it as, or we change that into x phi I, okay. And what is phi I? Phi I is nothing but instead of the normal xi, we are writing xy into x square plus y square. All right, initially our point xi just represented these two, okay, x and y, only these 2 points. But now we are saying that no, we would also put the third dimension over here, and therefore it becomes x square plus y square. And to separate the confusion, right, between xi and phi I mean sorry, xy and xy is and x square plus y square, we are representing it by a different entity called phi I and phi j, okay, phi xj. But the idea is quite clear, right? Initially it was not be separable using just 2D xi into xj, or for that matter xi and xj were not separable because they needed certain different decision boundary. So what we said that okay, let's put them into a higher dimension. So phi xi is nothing but that specific point in a higher dimension. All right, this is what I have shown. All right, so using this, we could use a decision boundary in the higher dimension, okay, in the higher dimension, to separate those points. But till now we have not used the concept of kernel. It was very simple, straightforward. We said that okay, it's not able, we are not able to separate them into using a linear decision boundary. We are not able to separate these points, so let's put these points at a higher dimension in which we can use a linear plane decision boundary in higher dimension to separate these points. All right, but you know what, it becomes a bit difficult to do when we have many more features, right now we are just talking about, let's say, one feature which we added, okay. So phi xi is nothing but we are saying that it is xi yi and then x square plus y square, okay. But what if, let's say, we are to add many more dimensions to it? So x square plus y square, we also add xy to it, we x cube plus y cube, etc, etc, right? So at that particular juncture it becomes difficult, right, to calculate xi xj, right? So what happens is you would consume space, right, for a single point xi. You would need to have, when you do the transformation phi xi, you will have to incorporate all those features, right? So this becomes many features. Okay, let's resume. So as I was saying is we have this xj, and we would be writing xj as, sorry, phi xj. Phi xj would also be written as something like, xj, then yj, and all these points. Now imagine if we have 100 such features, okay, and 1000 such points. So just imagine the storage we would need. And also what we would need to do is just that, not that we need to store, we also need to calculate the dot product of that, right? So we also would need to calculate this. All right, so there would be a lot of overhead. First of all, we will be storing these values, right, the extra dimensions, then we will be calculating the dot product, right? So it becomes quite difficult in terms of efficiency. So the scientists thought that is there any easier way in which we can do it without actually the need to store those values. So what they did is quite interesting. So let's do this. All right, so let's imagine we have these 2 points, okay, x y, okay, let's call it as some random point. Let's call it E, okay, and let's call this another point as F, okay, which is UV. And also let's talk about the transform points. So these points would be xy into x square and x square plus y square, okay, and then the other point would be f dash would be uv and uv square plus v square. So they said that, so as I was saying, the scientists did something pretty interesting. They said that okay, so what would be the end product of this, right? So if we are talking about phi xi transport into phi xj, okay, which is nothing but over here x, right, y, x square plus y, okay, so we are writing in matrix form, so let's call it x, y x square plus y square. So this is nothing but phi x, okay, and then we are calculating the dot product of this with the other point. All right, so this becomes u v u square plus v square, okay. So what is that dot product over here? So it's nothing but xu plus yv plus x square plus y square into u square plus v square, okay. So what they are saying is, with all due respect to this phi I and phi j, the end result can still be written in 2 dimension, okay. So this is what the actual kernel trick is. So please bear with me, I'll explain it once more. What we are saying is, this is what we needed to do, right, for the separation to be done in the hyperplane. But what we said that, okay, it is essentially costly to do that stuff due to 2 reasons. First of all, you will have to calculate all these different dimensions, okay, store it, and then secondly, you will also need to calculate the dot product of it, right. So that becomes quite humongous if we consider that there are many variables and at the same time there are many dimensions. So what they said is, okay, we need to do this, but what is the end result of this calculation, phi xi transpose into xj, right. So they did that, and what it essentially is, it's nothing but again something which appears into the 2D form, right. So you remember we said that there are 2 points, let's say these are xy, and the second point is nothing but uv. So you see the dot product of this, what we actually need for the optimization is nothing but again in 2D itself, right. So we need to actually imbibe this. So we are saying that, okay, the phi etc, the dot product etc we did, which was required, but essentially the end result is coming to be like this. So we took a longer route etc, but essentially we achieved this. So this is what is in 2 dimension. So this is what the kernel actually becomes. So the kernel is xy uv. So the kernel is nothing but, it's saying that it is equal to phi transpose xi, okay, into phi xj, and then it is nothing but xu plus yv plus x square plus y square into u square plus v square. So this is saying that, okay, you know, we actually don't need to calculate the phi xj every time. What we'll need to do is, we'll just calculate this kernel function, and the beauty of this is, this is nothing again but in 2 dimension itself, right. So for understanding purpose, what we do is, we tend to actually project it to higher dimension, find out the dot product for the dual optimization, but then to save space, save time etc, and make it more efficient, we say that, okay, what is the end result of this? We want to achieve this for sure, right. But instead of doing this, instead of going into hyperplane, calculating the dot product, right, can we actually do that without going into hyperplane? And we can actually do this because this is nothing but equal to this, right. And this is again something which we can easily calculate in 2 dimension only. We don't need to go into the 3rd dimension, right. So that's the beauty of this. So this is the kernel trick, right. So kernel trick is, what it does is, it actually does the task, right, which is actually exactly equal to taking the points into hyperplane and then separating them in using a linear decision boundary in the hyperspace, right. So this is what it tends to do without actually going through the 3rd dimension or the higher dimension. So you see over here, we are not going to the 3rd dimension or the higher dimension at all. What exactly we are doing is everything in 2nd dimension only. But how did we actually come to it? We said that, okay, we need to find out what is the higher dimension projection, calculate the dot product etc. We said that, but eventually found out what is the end result of this. The end result of this is again in 2 dimensions. So why not we just calculate this when we are actually trying to find the hyperplane and be happy with it, instead of projecting it hyper dimension and calculating the dot product. So that's essentially kernel trick, right. So what it tends to do is, without actually going into the higher dimensions, right, it tends to do what actually is being done by taking the points into higher dimension and segregating them using a hyperplane, right. So it doesn't do the projection, but it actually does what what the projection of the points at a hyperplane would do in a higher dimension, and separation of those points using a hyperplane would do, right. So that is nothing but a kernel trick, right. So we achieved that. Now let's come back to our original problem. Our original problem was our points was minus, I think it was 1 0. Okay, so let's write it as 1 0, B was minus 1 0, C was 2 0, and D was minus 2 0. Okay, So let's write corresponding kernel matrix for this. And why do we need it? Because our actual formula is alpha I minus summation of alpha I alpha j into into y I y j into xi transport into xj. So you see, we actually need it for each pair of points, and therefore we need to calculate the matrix for that, right? So that become our life becomes easy. So what we would, so this becomes what in terms of kernel, if I write, it would be alpha I minus alpha I into alpha j into y I y j into k x I and xj. Okay, so this is what we need to do. Now let's talk about what is when we write this. So this becomes, there's nothing but the kernel becomes a b a c and a d. Okay, then b a b b b c b d, then c a c b c c c d, and then it becomes d a d b d c and d d. Okay, so for all these points, right, whatever written, we need to calculate this, right? Xu plus yb. So also let me write what the kernel is. The formula for kernel which we found was xu plus py, xu plus yv. Okay, xu plus yv plus x square plus y square, no, x square plus y square into u square plus, okay, plus y square into u square plus v square. Okay, so for these points we will need to calculate this. Let's do this. So our initial point is 1 1, okay, 1 0. Okay, so if you do this, put this over here. Okay, what it becomes for our point a10. Okay, we are calculating this. Okay, which second points also become 1 0 itself. So xu. Okay, so let's write a equal to x into u. So 1 into 1, okay, plus y into v, which is 0 into 0, plus x square plus y square. Okay, so x square plus y square is nothing but 1, okay, into u square plus v square, again is nothing but 1 only. Okay, so what we arrive at as 2. So a is 2, a b. Okay, so a b is what? Our a is 1 0. Now b is, let me also write, a is 1 0, then b is what? B is minus 1 0. Yeah, b is minus 1 0. So let's do this. X into u is what? 1 into minus 1 is minus 1, plus y into v. Y into v is nothing but 0. Okay, plus x square plus y square. X square plus y square is nothing but 1, and then u square plus v square is also 1. Okay, so this becomes 0. Alright, so AB becomes 0 because x into u is this. Now let's calculate AC. Our C point is what? C point is 2 comma 0. Okay, so let's calculate AC. AC would be what? X u plus yb. So x u is nothing but 1 into 2, that is 2. Okay, plus yv would be 0. Okay, plus yeah, x u y plus x square plus y square into u s. Okay, so x square plus y square is what? 1. Okay, and then y square u square plus v square. 2 square plus 0 is nothing but 4. Okay, so this becomes 6. Alright, then we calculate AD. AD is nothing but, we calculate then x into u. Our d point, let's write it as x is 1 comma 0, d is minus 2 comma 0, right? So x into u is nothing but minus 2, okay, plus 5 into v is plus 0. Alright, and then x square plus y square is 1 into u square plus v square is 4. Okay, so again we get it as 2. Alright, so this solves the A part. Now let's look at into BA. We already know BA, we have calculated AB, so BA would also be the same. Now let's calculate BC. So we know our B point is what? Minus 1 comma 0, right? And C point is 2 comma 0. Okay, this is what we have now. B is minus 1 comma 0, C is 2 comma 0. Okay, alright, so let's do this. So minus 1 into 2, is nothing but minus 2 plus 0 into 0 is 2, 0 sorry, plus x square plus y square is 1 into y square plus u square plus v square is 4. Okay, so 4 minus 2 becomes 2. Then let's calculate BD. BD becomes this and D is nothing but minus 2 comma 0. Okay, so this becomes minus 1 into minus 2 becomes 2, then 0 plus 0 0, 1 square into 4. Okay, so this becomes 6. Alright, similarly let's calculate, okay, we also need to find what is BB. So BB is nothing but, again let's write it minus 1 comma 0. So 1 into minus 1 into 1 plus 0 plus 1. Okay, because this x square plus y square 1, and then z square v square plus v square is also 1, so this becomes 2. Alright, let's calculate CC. CC would be, again let's write is C is equal to 2 comma 0, right? So it becomes 2 into 2 4 plus 0 into 0, right, is equal to 2 comma 0. It becomes easier for me to visualize. Right, so x into u is 2 into 2 4, 0 into this, plus we have 4, okay, into 4, okay, 16 plus 4 is nothing but 20. So we get this. Also let's write CD. CD would be nothing but C is this and D is minus 2 comma 0. So we get as 2 into minus 2 is minus 4 plus 0 plus 4 into 4 is nothing but 16. So we get it as 12. Okay, and then DD. Okay, DD is nothing but this is D, again D, let's write as DD. So D is minus 2 into 2 minus 2 4, 0 into 0 plus 4 into 4, which is 20. Okay, so let's write what our kernel is. Our kernel was AA. Okay, AA is nothing but 2. Okay, now what is AB? AB is nothing but 0. What is AC? AC is nothing but 6. What is AD? AD is nothing but 2. Okay, now BA. BA would be the same as AB, which is 0, and then BB is what? 2. Okay, BC is what? BC, we have not calculated. BC is 2. What is BD? BD is 6. And then what is CA? CA is nothing but AC, which is 6. Okay, let's write it as 6. Then BC is equal to CB equal to 2. Okay, CC we have calculated and this is 20, and CD is nothing but 12. Okay, so now DA is 2, DB is 6, DC would be again is equal to CD is equal to 12. Okay, and DD would be nothing but 20. All right, so we get this is our kernel, right? Again I reiterate what a kernel is. Kernel actually tends to without actually pointing or without actually taking the point to a higher dimension and then using a hyperplane to separate those points in the higher dimension, what it does is it does all that stuff without taking the points into the higher dimension. Because kernel is nothing but what we tend to do is find out what is the mathematical formula pertaining to or which is equal to the process of taking those points at a higher dimension, right, and using the plane to separate them, right? So that those function what it is there, right, it is actually being equated to the kernel function. You remember what we did, what the kernel was? So if you go over here, we said that okay, this is what the thing is, taking the points into higher dimension and doing the dot product of this. So what is the mathematical representation of this into 2D or into the lower dimension? So we calculate that and then we say that okay, we won't be going into higher dimension and calculating the dot product into higher dimension, but instead we will use the formula of whatever this task is, right? So this eventually corresponds to the formula this. So we say that okay, we won't go over here, we'll just work with this because this is nothing but equal to 5 t into 5j, which is nothing but taking the points into higher dimension and calculating the dot product. All right, so then we arrive at this. Now what? So what we'll do is, now let's go back to our original point. Okay, so our original point was like this. This was what? This was 101. Oh, sorry, this is some issue with this. There's nothing but 1 0 and 1. Okay, and then our second point was minus 1 comma 0 comma 1. All right, and then what we said was our point would be in higher dimension, which would be 2 comma 0 comma 4. Okay, and then this point would be removed. Okay, we'll need this in some time, so let's say, oh, let me do one thing. Sorry, I should be more conservative with the space, but never mind. All right, so let me go back over here. All right, let me make it clear. So this point was, let's say 1 comma 0 comma 1, and then this point after projection became minus 1 comma 0 comma 1. All right, and then we also had this point, okay, which would be 2 comma 0 comma 4. All right, and then this point would become minus 2 comma 0 comma 4. All right, so this is what we done at the projection. Now these are the decision points in the decision boundary, because both of them show that, okay, this is belonging to the negative space, and this is belonging to the positive space, this is belonging to the negative space, right? So these are the support vectors, and if you were to draw a line using this, so this is what a support vector would look like. All right, now what we essentially need to find out, what is the equation of this plane, okay, which is parallel to these two lines, right? And such that this margin, this is called, this actual distance is the margin, such that the margin is maximum. Okay, so we needed to find that out. So what we'll do is, if you look at this decision boundary, if you look at this, right, so what is alpha? The alpha over here is, when we talk about the support vectors, it actually means that how powerful that point is in terms of deciding what the decision boundary would be, right? I repeat, alpha actually dictates how critical that specific point is, right, for which we are calculating the alpha, is in terms of dictating how close to that point, right, how close to that point would the separating line be. Now if we look at this, if we were to look at this minus 2 comma 0 comma 4, 2 0 comma 4, these two are nothing but the identical twins. So if you imagine z axis, right, z axis to be a mirror, then these 2 points are nothing but the identical twins. The distance, etc., everything is same over here, right? Minus 2 comma 0 4, 2 comma 0 4. So these 2 points are essentially having the same power of attracting this decision boundary, right? So which we can say, then we have, let's call it A, B, and then let's call it as C and D. So alpha C equal to alpha D. All right, and then similarly we'll have alpha A is equal to alpha B, right, because the same situation gets replayed into the A and B as well. So I again repeat as to why alpha C is equal to alpha D, is because see, the point alpha dictates as to how critical that specific point is in terms of deciding how closer that decision boundary, right, would be to that specific point. But in this case, minus 2 comma 0 comma 4 and 2 0 comma 4, right, are nothing but identical, right? If you put a x-axis or an line perpendicular to them, both of them would be at the same side, right? So these two have got exactly the same attracting power, if I may, to this line which is dividing them. Therefore alpha C is equal to alpha D, and similarly alpha A is equal to alpha B. Now if you remember, when we are trying to optimize the SVM, we also said that for all the points related to this, we have alpha I into alpha y equal to 0. All right, this was done after differentiating, right? So we got this specific equation, summation of alpha I minus alpha if you write alpha I and j, and then we had said alpha I, alpha j, and then yi into yj, and then we had write xit into xj. Okay. Sorry, not this point. So the original equation was something else, right? The original equation was, if I recollect it nicely, it was the optimal, that's like the Lagrange's thing, right? So it was half of w square, right, minus summation of alpha I, and then we had written alpha I into w transpose xi plus b minus 1 equal to 0, right? So if we differentiate it with different terms, first with w, right, and then once with b, right, we'll get the equation, right? So we tend to get at alpha I into yi once we differentiate it with, you see, if we differentiate it with respect to b, all right, we'll get summation of alpha I into yi equal to 0, right? So this is one of the equations which comes in handy. So in our point, right, we have alpha A equal to alpha B is equal to, let's say, A, and then alpha C equal to alpha D, sorry, what is this, equal to B, right? So if we do this, so we will get as alpha into yi. Now what was yi? Yi for A and B is what? Plus 1, okay, and then alpha C, alpha B is, so we will also write A into 1 again for the second point, which is B. Now if you write for C, it becomes B into minus 1, and then for D also it becomes B into minus 1, right, because alpha C is equal to alpha D equal to B, and the point yi, right, the label of that was minus 1. So we get it as 0, which is nothing but A equal to B. So you see, now we are saying that alpha A equal to alpha B, which we already knew, is equal to alpha C equal to alpha D equal to, let's call it as T, okay, right? So we get this. All right, so where were we? So if we look into the dual optimizer, what we had was alpha I minus summation of ij, and then we had written alpha I, alpha j, yi, yj into xi, sorry, into, let's say, kxi into xj, okay. This is what we had. Now if you look into this, this is alpha I, all alpha are equal, and we are talking about 4 points, right? So this becomes 4t, right? This, if you extra elongate that, it would be alpha A plus alpha B plus alpha C plus alpha D, because we are talking about summation, each alpha is same, so it would become 4t minus, now we know we had already calculated this point, okay. So this is the vector form which we calculated. So if we were to write it as, and this C, alpha I and alpha j both are same, right? So we can write it as t square. Okay, let's take all those constants out. Alpha I, alpha j all are same, so we can take it out. It is t square, and then what we have is xi xj. So let's write it over here. Xi xj was a lengthy term. Okay, this one 2062. Okay, let me write it as 2062. 2062 0226 6 to 2012 6 to 2012, and then last is 26 1220. All right, so what we have is this, but at the same time we have not taken into consideration yi into yj, okay. Now if we talk about this specific point, right, which is nothing but aa, over here the label would be plus 1 into 1 plus 1, because the label for point A was plus 1, same for B is equal to plus 1. The label I am talking about, C is minus 1 and D is minus 1, okay. And if you recollect, this point 2A was nothing but, as I had shown earlier, it was AA, right, calculation of AA, then AB, AC into AD. So now think from that perspective what this number is. So this becomes plus 1, right, so plus 1 into plus 1 is plus 1. Similarly for B is plus 1 into plus 1, which is again plus, right. For the other point, right, C, it is AC, so A is plus, C is minus, so this becomes minus. Similarly, a is plus, d is minus, so this becomes minus. Now we talk about b. So for b, this point and this point both would be plus, right? Again, b and c are of different labels, so this would be minus, this would also be minus. Now the reverse would happen in case of this row, because this pertains to c row. Now c and a are negative, are opposite levels, so this and this becomes minus, this becomes plus, this becomes plus, this becomes minus. Again, d and b are of opposite labels, this becomes plus, this becomes plus, right? So what eventually we have is, if you sum this up, minus 2, 2 minus, so this is minus 6, plus this row is minus 6, plus, okay, so this is 24, minus 2 minus 6 is minus 8, 12 minus 8 is 12, 12 plus 12 is 24, then minus 2, 6 minus 2 minus 8, 12 minus 8, 4, this becomes 24, right? So if you sum this up, 48 minus 12, which is nothing but 36. So eventually we get the kernel is nothing but 4t minus t square into 36, okay? And we want to maximize alpha into this. So remember this form, how did we get? This form is, so this is not the kernel one, this is actually the dual, which we had already get, the dual optimizer. So dual form of the equation was this, right? So what we had done was, you see, earlier we had this equation, this one, alpha I minus alpha I, alpha j, alpha this, and this is what we got by Lagrange's, and then we had differentiated, we got w, we supplanted w into this equation, and we arrived at this, right? So the initial optimizer was this, sorry, y I y j k, right? This was it. And when did we actually did solve this, right? So alpha I, we said that all of these are same, and I explained the logic. So this becomes 4t minus alpha I, alpha j, both are same. So alpha is square, we said it is, let's assume it to be t, so it becomes t square into 36, etc., right? Oh, and at the same time I forgot 1 by 2 was also there, right? So in the formula, sorry, my bad, it was 1 by 2 as well, so we forgot that. So let's write it as 2. So this becomes 4t minus 18t square, right? So we want to maximize alpha in the sense that we want to maximize t. So what we will do is, we will differentiate this particular function with respect to, let's say, df by dt. So this becomes 2t minus 36, sorry, this becomes 4 itself, sorry, my bad, 4 minus 36t, okay, equal to 0, or t equal to 1 by 9. All right, so what we are saying is, alpha a equal to alpha b equal to alpha c equal to alpha d equal to 1 by 9. All right, okay, so this was it. And then what we'll do is, we will then try to find out what is the equation, right? What is the equation of, okay, so let's first of all find out what this optimizer is, what the dual becomes, okay? Dual is what? 4t minus 18t square, okay? So 4 into t is nothing but minus 18 into t square, 1 by 9 into 1 by 9, okay? This is what it is, no? All right, so this is 4 by 9 minus 2 by 9, okay, which is nothing but 2 by 9, okay? Okay, so now this is fine, finding this value, but what we are really interested in is in finding the decision boundary, right? So if you recollect from the past, let's write this equation, okay? What was the Lagrange's equation? It was half of omega w square, okay, minus it was summation of alpha I, and then we had written yi into w transpose xi plus b minus 1 it was greater or equal to 0, right? And we had calculated it, we had differentiated with respect to dw. So let's do it as again, dw is nothing but w minus summation of alpha I yi into xi becomes 0, okay? And then we have w equal to summation of alpha I yi into xi. and in that equation what we had written was our plane of separation was, equation of that was nothing but wtx, okay, plus b equal to 0. B was a general point, so this was our equation, all right, and we had got this alpha. Now let's just do this, okay. So for our kernel equation, let's take okay, point A. Point A is what? 1 comma 0, and we know the label of this is plus 1. So if we take this, right, so our w is what? Our w is, so let's write it over here. So it is nothing but summation of alpha I into yi into, okay, let's write it xi, and then it becomes xj plus b equal to 0. All right, this is for point A. All right, and this is, we could write it, right? We could write it because this is the point, this is the equation of that point, and we essentially want, sorry, there was this mistake because we are talking about point 1, so it should be equal to 1, right? Because this is a and b, this was 1 comma 0, this is minus 1 comma 0 comma 1. We are talking about that, let's imagine this in hyperplane, and then we are saying this is c comma d, okay, which was 2 comma 0 comma 4, and then there was minus 2 comma 0 comma 4, sorry, it disappeared. Okay, minus 2 comma 0 comma, this was 2 comma 0 comma 4, right? I'll write it over here so that it is 2 comma 0 comma 4, and then it was minus 2 comma 0 comma 4. Now we are talking about this point, right? So because this is on the positive side, we, and this is a hyperplane, right? This is a hyper, this is, sorry, is the is the point which is line which is passing through the margins. So if you consider about this, this is w transpose x plus v equal to 0, okay. This is on the positive side, so we write it w transpose x plus b equal to 1, and this is w transpose x plus b equal to minus 1, okay. So using this we write, okay, over here, and now for point A, all right, we know alpha I is what? We know alpha is 1 by 9, and we know the label of y I, right? The label of y is also 1, and then what we do is summation of x I, sorry, it is kernel over here, right? Kernel over here, kernel of x I, and then xj plus b equal to 0. Now for this specific point I, we already know, right? We have selected already fixed I, but j is not there. So we are talking about the kernel corresponding to the point A. Okay, and if you remember, the kernel corresponding to point A was, you see, this one. Okay, the kernel corresponding to is minus 6. Okay, so what we write is like this. So it is 1 by 9 into minus 6, all right, and xj we already knew, it is nothing but I mean, this is the kernel which we calculated for this specific point, plus b equal to 0, and b then becomes nothing but 6 by 9, which is 2 by 3, okay. So this is done, we have already found out b. Now our major challenge is this one, okay. We need to find out w, which was nothing but alpha I, okay, into yi into xi, all right. But in our scheme of things, right, because we have considered kernel, it becomes summation of alpha I, and sorry, there were two mistakes over here. First of all, let me fix this. B equal to 0 wasn't there because we are talking about one point A. For this it was b is equal to 1, so it would become 5 by 3 first of all, alright. Now what we are saying is this, so let me also draw this. This is A, this is B, alright, this is the decision point, so we will write w transpose x plus b equal to 0. This is nothing but w transpose x plus b equal to 1, and w transpose x plus b equal to minus 1, okay. This is minus 1, so we need to, let's imagine this is the point which we need to find out, and therefore we'll write the kernel corresponding to the point lying on A, lying on this specific line, right. So for that what we'll write is, for w it becomes summation of alpha I, okay, which is fine, and then what we'll write is k of, now this is very interesting, this is a generic point which we know, which we want to find the equation about, so we'll write it as k, but the other point is a, right? Anyone you can take, either can take a, b, c or d, so for simplicity I take it as a. Okay, so this is what we need to find out, and then we'll equate it to be equal to 0. All right, and for here we already know what is alpha I. We know alpha is 1 by 9, right? For so different alpha I, it become 1 by 9, 1 by 9, 1 by 9, 1 by 9, right? So now let's figure out what k of xa is. Now again the task is similar to what we had done. It's a slightly tedious word, but we'll take it as it comes. So a, we know x point is, let's say x comma y, this is a generic point, and then a is 1 comma 0. Sorry, this is a bit complex, right? So I tend to commit mistakes while explaining this. My bad. So see, the W was over here. It is summation of alpha I, okay, and then it was earlier xi xj, right? Now we write xi xj as over here like this, right? And plus b we already have. This would be equal to 0. All right. Now the thing to be noted is this x and j, right? They are changing. So let's write it as this, right? So they are changing. So first of all, we will okay, xi is constant. Xi is constant in the sense that we are just calculating it for a point lying over here, right? So we are not varying it. This point remains as over here. We need to find out the kernel of this point along with these C, D, right? These 4 points. So essentially it becomes nothing like alpha I into, then it would be k of ax, okay, then plus okay, we can write it over here, then k of bx, then kernel of cx, and then kernel of dx. Okay, this is what plus b equal to 0. Okay, so let's write plus b equal to 0. Okay, so what is kernel of ax? We already found out that the kernel formula is nothing but xu plus yv plus x square plus y square into u square plus v square. Okay, this is what we had found out. Now our a point is what? Our a point is 1 0. Okay, so let's quickly write what of k of x would be. Okay, so k of ax would be x into 1 is x, y into v is 0, x square plus y square. So let's write it x square plus y square. Let it remain as it is, and u square plus v square is 1. Okay, so this becomes this one. Alright, so this is a of x, k of b of x. Okay, so b is nothing but minus 1 0. Okay, so this becomes b. So x minus x, this becomes minus x. Okay, plus y is 0, plus x square plus y square into a square plus b square is nothing but again 1 x square plus y square only, right? So this remains as it is. Let's write it as k of k of c of x. Okay, so k of c of x, we know c is nothing but 2 comma 0. Okay, so x into 2 is, okay, so x into 2 is 2x. Alright, plus yv is nothing but again 0, plus x square plus y square. X square plus y square still remain as it is, but now we have u square would become 4. Okay, and v square is 0. So this is that, and then we have k of d of x. K of d of x is would be what? Now let's say k of d is minus 2. Sorry, minus 2 comma 0. So let's write this. So x into minus 2 is minus 2x. Okay, plus y into v is again 0, plus x square plus y square would be x square plus y square itself into y square plus is 4 minus 2 square plus v square is 4. Okay, so you see what happens is this gets cancelled out. Okay, this and this gets cancelled out. If you do the summation of this and this gets cancelled out. So all we are left is this one, right? We are left is this 4 plus 4 8 plus 2, right? So we are left with 10x square plus y square. All right. And then over here what we have is summation of xi. Okay. The summation of x square is what? It was, you see, an alpha I. So this would become, all right, alpha I we can take it as common. Okay. So this becomes 1 by 9. Okay, so we have this again. Sorry, there was a mistake over here. It's so complex, right? It's very easy to commit mistakes over there. My bad. So see, let me just remove this for the time being. Okay, so let it remain as it is. We know what it is, akx. Okay, so let's write it as akx is what? Akx is yeah, x plus x square plus y square. Okay. B kx was what? Minus x plus x square plus y square. Okay, which is fine. C kx of was what? C kx was 2x plus 4 x square plus y square, and then d kx was what? It's equal to minus 2x, right? Minus 2x, correct? Plus 4x square plus y square. Alright, so the mistake I made was earlier in the summation, right? So what the function fx would be, what does it say? It says alpha I, okay, into yi into k of xij, okay, xj. Alright, so now what I did was alpha I had taken out because this was common, so 1 by 9 was there, but I forgot that we also need to consider yi, right? So for point A and B, this becomes plus, right? So we could write, if you do this, this is into 1, okay, into 1, okay. So in which case this becomes cancelled. So eventually here we have 2 of x square plus y square, which is fine. But then if you look into this, this becomes minus, okay. So this is into minus and this is into minus, okay. So it eventually becomes minus 2 of x minus of 4 x square plus y square, okay, and this becomes what? Minus of, sorry, plus 2 of x minus 4x square plus y square, okay. So if you sum these up, this cancel out, but this becomes minus 8, okay. So this would be minus of 8 x square plus y square, and obviously we had the b term as well, and b term was what? B term was 5 by 3, okay. Equal to 0, okay. So this becomes minus 8 plus 2, 2 minus 8 is minus 6, okay. So this becomes minus 6 by 9 into x square plus y square plus 5 by 3 equal to 0, okay. So this becomes minus 2 by 3, you can cancel by 3. So eventually what we are left is minus 2 of x square plus y square plus 5 equal to 0, or x square plus y square is equal to 2 by 2.5, 5 by 2. Now what does this mean? This essentially is saying that for our original point, which was this, okay, 1 comma 0 minus 1 comma 0 and then 2 comma 0 and minus 2 comma 0. x square plus y square is equal to 2.5. That is this specific circle, right, can be used to classify this point, so segregate these points, right. So this is belongs to minus, this belongs to minus 1 category, and this belongs to plus 1 category, right. So the entire, sorry, this is minus and this is plus 1. So this entire exercise was to use the linear form of kernel which we had got, right, that is initially summation of, which involves xi into xj, and then what we said that, okay, can we use a linear, can we use a kernel function, right, to actually help us convert the decision boundary into a circular one. So what we did was, we first of all converted into higher dimension, and then we used the kernel trick to convert it into a circular boundary, right. So this is what the kernel trick was, and this efforts is really fantastic, which helps us understand that how we can use a kernel function as a proxy for putting the points into higher dimension and taking their dot product. So this is what the kernel trick is. Thanks for your time.